Okay, here we go. 1.2 volumes. And this should be a pretty clear continuation of the stuff you probably did at the way end of your AB class last semester. And so we're going to carry on with sort of cross sections. And so it says, remember problems like these? Example, find the volume of the solid generated when the region bounded by this function, which I've graphed here. So the region bounded by this function, the x-axis, x equals -2, and x equals 2 is revolved about the x-axis. So let's see, here's -2, or x equals -2. Here's x equals 2, more or less. And so we can kind of see the region that is bounded. And we're going to, pen, please. And we're going to rotate it about the x-axis. So why don't I just kind of carry this down a little bit and just extend that down a little bit. And when we kind of basically reflect it down, and whatever, close enough. So that would be, basically what you're looking at, except three-dimensional, and like this is kind of rounded, and this is kind of rounded. Basically that three-dimensional sort of shape going on. Anyway, so moving on to the reading on the right here, you may have found the volume of solids like this by slicing it up into disks and simply adding up the volume of those. Using a definite integral, the volume was exact because then the thickness of each disk was limiting to 0. However, you can just think of a super thin disk as a circular cross section of area. I guess you can just think of it in terms of area, the cross section of area. And the volume of the whole solid is going to be the integral from A to B, wherever to wherever. And you just integrate the area of, like a typical cross section. This A of x function that represents the area of any cross section throughout the solid, and dx. And basically dx takes care of that whole change in x, infinitely thinness of each disk, circular cross section. And I think in 2019 here, the students had Mrs. Clute. I think she does sort of emphasize how, the whole disk verbiage, but also just like a circular cross section of area. And that's basically all you need to do is integrate, the area of whatever cross section you're talking about, either dx or dy. Let's actually do a problem here. So the next part of the notes talk about this example. Find the volume of the solid generated when the region bounded by that function, just a parabola, and y equals 2. So let me cheat a little bit there. I'm drawing this straight myself. So that's what we're kind of looking at. basically between the parabola and y equals 2. And once again, we're rotating it about the x-axis. And so when we spin the x-axis, that area sort of rotates down, and we're essentially going to have something that looks like that from this point of view. I mean, kind of have like this sort of thing going on. Ooh, that's not that good. But, you know, we're kind of just spinning this kind of thing. And so when you think about a cross section of this guy, we're going to be talking about a washer. And this should be familiar when you think of last semester. So here's what I'll draw as like a typical washer. Okay. I can draw it a little bit better probably. So there's like a typical washer at a random spot, you know, throughout the solid. And if you remember from last semester, the area of this washer, it's basically like a disc with a, or it's like the area of a circle with a circular hole in it. So you just have to do the area of the entire circle, which is going to be pi r squared, but more specifically, pi times the outer radius squared. Like from here to here would be like the radius of the entire circle. So pi outer radius squared. But then you have to subtract the area of the hole, which is going to be, again, pi r squared, but this time the radius is like the inner radius. And so when we set up this a of x part, the outer radius, like from here to here, is always going to be 2. So we have, and I'm also factoring out the pi. Okay, you can like factor out the pi, which I'm doing here. And so the outer radius is 2, so 2 squared. And the inner radius, which is from here to here, since it's just from the x-axis to this parabola, we can describe the inner radius as the function 2x squared. Okay? And this can even be simplified a little bit more. You know, I mean, you could throw this into your calculator if that's what you're using. I mean, you might as well use your calculator to make things easy if you're allowed to. And you could throw this into your calculator, or you know, this. It's a little more simplified. But so we integrate, right? And we're going to integrate this from wherever to wherever. So I think we're going to bring the pi out. And so, you know, the rest of it, 4 minus 4x squared, can go here. This is what we're going to integrate. And like as we talk about like the infinitely thinness, you know, it's going to be a change in x. And by the way, you know, everything's got to match. If whatever you're integrating is in terms of x, you know, just look, here's an x variable. If what you're integrating is in terms of x, it's got to be dx. It's got to be in terms of x, or with respect to x. And these values right here, your limits of integration, have to be, you guessed it, x values. And that makes sense because as far as like adding up all of these washers, it's like the first washer, it's going to be, you know, washer, 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 washer. These washers are stacked side by side, and it's like the first washer's way over here, and it goes all the way to like the last washer, so to speak, over here. So basically from here to here, we're adding up these washers, and that definitely, you know, correlates with it needing to be x values. So it looks like it's going to be from -1 to 1, we're adding up washers. And so when you throw this into your calculator, and you might want to do that really quick, pause the video. Make sure you can get 6.4 and then the pi out here. 6.4 pi, which you could easily approximate if you needed to. And that should be pretty familiar, but I don't know if this will look familiar at all, where, guess what? Your cross-sectional shapes don't have to be circular. They could be squares, they could be triangles, whatever. So in this case, the situation set up here, a pyramid 3 meters high, which means right here, from here to here on this x-axis basically. So a pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. So 3 by 3. 3 by 3. Each cross section of the pyramid parallel to the base is a square, just like this red one right here. This red square. Find the volume of the pyramid. Now I know we can just probably do this with like good old-fashioned geometry and it's a pyramid, but if we were doing this calculus, style, we would integrate the area of any typical square, like integrating a sort of function that represents the area of any of these cross-section squares. And looks like it's going to be change in x as we go from square, 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 cross-section, cross-section, cross-section. Looks like it's kind of a change in x. So it's dx, which makes sense because we're integrating from like your tiniest square, your first square, pretty much all the way to the base. And so that's going to be from 0 to 3. And so what's the area of a square? Isn't it basically, in a way it's length times width, but it's a square. That's a very specific sort of rectangle where length and width match. And so you can just say it's like, say s squared, And I guess there's a lot of spoilers already here in the picture. What's the side length of any one of these squares? It's just going to be x. I don't want to over-explain this or drag us too slowly through this problem, but just the way this is happening, if you're over here at 3, then the square is 3 by 3. If you drew a square at 2 on the x-axis, then it would be a 2 by 2 square. If you drew a square over here at 1 on the x-axis, it would be a 1 by 1. Basically, like wherever you draw your square, the square sides are going to match like whatever the x-coordinate is. So basically, any given square is just going to be x times x. Like whatever this x-coordinate is, x value, it's going to be that x times that's, what I mean? So you can just call it x squared. And so that's what we're integrating. No pi's because it's not a circle, it's a square. And whatever the shape is dictates the area sort of formula or function. And I guess I did this the long way, where you actually integrate, sort of by hand, and then we're going to plug in the upper limit, 3, and then we're going to plug in the lower limit, 0, and just subtract it. And ultimately you get 9. If you want to double check that on your calculator, feel free. I got 9. And so yeah, sorry, but we can do any kinds of cross sections. Like this next example, where the setup gets a little bit heavy on the verbiage. A lot of fancy reading here, so hey, I highly recommend reading it again, reading it a third time, making sure you understand what's going on with this this solid with volume, and the cross sections and everything. So a mathematician, which shall remain nameless, has a paperweight made so that its base is the shape of the region between the x-axis and one arch of the curve y equals 2 sin of x. That's in black. y equals 2 sine of x. Looking at the picture that I have here, the function or for y equals 2 sine of x, that's in black. Each cross-section cut perpendicular to the x-axis, is a semicircle whose diameter, not radius, diameter runs from the x-axis to the curve. Find the volume of the paperweight. So really quick, it's important to point out that semicircle literally means half circle, like exactly half of a circle. And yeah, so look, I mean, so is it going to be dx or dy? Change in x again. So this is going to be a of x. And so we have to represent the area of a typical cross-sectional half circle. Okay? And look, you should know enough coming out of the first semester about the graph of 2 sine of x. This shouldn't be that much of a spoiler that, you know, this is 0, obviously, and this value right here where the arch comes back to meet the x-axis, this is pi. So as we add up the areas of all these half circles, we're going from basically, too much of a spoiler alert, crap. At least the limits here, we're going from 0 to pi. But, okay. Now how are we going to find the area of one of these circles? Well, once again, it's literally a half circle. So that's why you saw there, as a sneak peek a second ago, 1/2, you know. So we're going to do pi r squared for the circles, for a circle, for all the circles. It's weird talking about this. But, so we are going to do pi r squared, but we're going to have to cut it in half because it's not a whole circle, it's a half circle. So this is going to be r. We got to do r squared. So what is going to be the radius of a typical circle here? Right? I mean, remember, it's not diameter, it's radius. I mean, looking at this, I hope you realize fairly quickly that the entire diameter you can represent as the function because it's going from the x-axis out to the curve, you know what I mean? So the entire diameter is basically 2 sine of x. But since we just want the radius here, we have to basically divide that in half. So the radius is going to be 2 sine x divided by 2. So we have pi r squared, but then we have to, because the whole half circle thing, we have this half, and dx, you know. And basically, that's pretty much most of your heavy lifting here. Because from here, you're just going to throw it into your calculator, probably, and get, well, here's a little bit of cleanup first. Sorry. If you square, well, basically these 2's cancel out. That's probably the best way to do things here. The 2's cancel out, then we can square the sine of x. So maybe you want to throw this into your calculator. And once you multiply everything, you know, 1/2 times pi times the integral of this from 0 to pi. This is what at least your approximated answer should look like. Okay? Moving on. Now, I mean, I guess all this stuff was pretty new, especially using squares and whatnot, but this is absolutely, for sure, going to be new to us. So if you need to pause the video and get this picture drawn, I mean, whatever, but here I'm going to move on here. So this part of the notes is called using cylindrical shells. This is going to be a completely different method than your discs, washers, squares, which are all essentially cross sections that have area and, and when you factor in the whole dy dx thing, dx or dy, it actually has like basically volume, but this is completely different than like a cross-section area. So here we go. Well, first of all, let's address the picture and everything. So here, I'll get to this in a second. So what we're doing here in the example is we're going to take the region enclosed by the x-axis and this parabola, which is right here. This is the parabola, or at least part of it, between here and the x-axis. And so here's our region of area between the parabola and the x-axis. I mean, I could basically draw that. And so there's the region of area. And what the problem says is we're going to revolve it about the line x equals -1, which is right here. X equals -1. So if you spin this, then this sort of reflects over here. Remember, you're also reflecting this gap of space. So there'll be another gap of space right here, and then, anyway, if I were to give this problem to you at any point prior to now, you would probably look at this as a washer problem, wouldn't you? And I'm gonna draw a washer, but don't draw this because we're not gonna follow through with this. I'm just gonna show you something really quick. But I'm gonna erase this in a second, so don't draw this washer with me. Especially not that crappy looking washer. Whatever. I should just cheat and use the circular tool, shape tool. So, I mean, if you're talking about, okay, we're going to do outer radius squared minus inner radius squared. I mean, look at this. The outer radius and the inner radius are controlled and dictated by the same curve. And you're probably thinking, how would that work, setting up the integral for the washer? And basically the answer is, it wouldn't work. It wouldn't work. So, long story short, too late. Washer method, cross-sectional method, doesn't really work in this example. Doesn't really work. And so we're going to teach you about this other method which involves cylindrical shells. And in class, if you have me teaching to you live in person, I have the advantage of like grabbing like a piece of paper and rolling it up right in front of you and showing you what a shell is. But maybe I'll just draw one really quick. And so here is like a typical shell. God, I am such a... Ugh. Okay. And I mean, it does have like an infinitely thin sort of thickness to it. But again, this is like hollow. It's basically a cylinder, just like the outer shell of a cylinder, really. Completely hollow. It's like rolling up a piece of paper in a tube, basically. You might as well call it a tube that is like infinitely thin, right? And so instead of slicing this solid, this three-dimensional solid up into like discs or washers, we're going to have these shells that work their way from the inside and they work their way to the outside like tree rings, and they're all going to kind of fit inside each other. So I'm going to draw another shell. I don't think you should muddy up your picture. So don't draw this other shell like I'm going to, but in the innermost shell would be basically here, working our way outward from the middle out until like one of your outermost shells would be like out here. Again, don't draw this unless you really, really want to. It's probably just going to complicate your picture a little too much. So there would be like one of the outermost shells. And again, usually, I draw it so that it kind of has a somewhat thickness to it, but not that much. And so that would be one of the the more outer shells. But if you were going to draw one of the more inner shells, it would look like this. Okay, so again, it's this infinite number of shells that are working from like the inside out, basically all fitting inside of each other. Ooh, I feel like drawing this picture where they all look to be... Yeah, you know what I mean? So there's like an infinite number of these shells, right? And we're going to basically add up the volume, this is essentially like finding the volume of a piece of paper, because if you unravel this tube, it's just going to be, like I show in class, like a piece of paper that's rolled up. Well, if you unroll it, it's back to being a very, very, very thin piece of paper, rectangle, basically, is what I should be saying. If you unravel it, it's basically a rectangle that is, length times width, but it has like a very, very thin thickness to it also. But I guess I shouldn't call it length times width, because with the shell, it would be like length times height. Like we're going to call it the height of the rectangle or the shell. And the length of this rectangle is basically going to be, like if you unravel this, the length is essentially the circumference of that circle. Anyway, let's cut to the chase. Without any more further ado, what is the volume of any shell? Well, it's going to be 2 pi times the shell radius times the shell height, essentially the width of the rectangle, times the shell thickness. It's not much of a thickness, though. That's where dy or dx comes into play. dx or dy, whichever one. If you want to change the order, I wouldn't blame you. The shell thickness in our integral is going to be represented by dx or dy. And this 2 pi times r, 2 pi r. What does that remind you of? Circumference. But all of this in blue is essentially the volume of any shell. Okay? And so we're going to set up our integral where we integrate that. Okay, so how do we throw all this into an integral? Well, 2 pi is just going to be 2 pi. And the radius of the circle of the shell, basically. Now listen to this part. You might even want to write this next, what I say next. You might want to write it down in your own words. The radius part in your integral, we're always going to define very, very simply. We're not going to use a function in the graph. We're just going to define it basically as like x or y, or in this case, this horizontal line segment if I were to call this just x, it would be almost correct. Because isn't x from the axis out to the curve, isn't that going to be like some x coordinate, some x value? So just saying, like, this is x from here to here, that's x. For the entire radius to be described, wouldn't you have to say it's x plus this other length of the segment, this other part? And so in this example, our radius is not just x, it's x plus 1. And so again, your radius is always going to be described very basically. Very basically. What am I doing? It's the height that's going to get described using the function. Okay, so here's the height, which, in this example is just going to go from the x-axis to the curve. And again, if it's going from the x-axis to the curve, we can just describe it as the function 3x minus x squared. That's the height of any of those shells. And, I mean, at this point, it's pretty obvious that if it's going to be dx or dy, because, again, x plus 1, 3x minus x squared. These shell thicknesses, and again, this is easier in person for me to pinch my fingers together and show you, but, the thickness, like right here, thickness, of each shell is a change in x. Also, or over here, whatever. Kind of going like left to right here. The thickness of each shell is dx, change in x. And even more evidence is like these limits of integration right here need to be, and they're going to be, x values. And so here's the thing. Now listen. Just like with discs and washers and square cross sections, whatever, we're going to integrate from the first shell, or in this case, like the innermost shell, to the last shell, or like the outermost shell. Now look, the first innermost shell is not here. It's here. Like, that's the first shell. That's the innermost shell right here. So right here. So we're going to start our integration from here all the way shell, 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 until the last shell right here. So we're going to be integrating from 0 to 3, it looks like, which is like from the first shell to the last shell. And again, those need to be x values. And now you're ready just to throw this into your calculator and get exactly 22.5 pi, I believe. Feel free to fact check me on that, but looks like we're going to do one more example with the shell method. So the region bounded by the curve y equals root x, which I already have drawn here. The x-axis and the line x equals 4. 1, 2, 3, 4. So there is the region of area that's going to be revolved about the x-axis. Okay? Which means the entire 3D solid is going to essentially, look like that, basically. And hey, at least this one time. Whoa, whoa, dude. Didn't think it was going to be that big of an eraser. I'll leave that middle part, because yeah, we're going all the way to all the way to there, all the way to 4. You know, now, normally, right, I kind of like that picture, but normally you would do this with just discs or like circular cross sections. And of course, in the grand scheme of things, I wouldn't blame you if I gave you this problem. You know, so basically, this example is definitely not an example like this, where you pretty much had to use shells, otherwise you were dead in the water. This problem you can totally do with discs, but we're going to do it with shells, just so we get another example of seeing how the shell method works, okay? So, but we have to kind of draw a shell. Now again, these shells are going to work from like the inside out. So like the innermost shell is basically going to start in the middle, but you know, as we expand from the inside out to fill all of the... Wait, should I be going all the way there? No, I shouldn't, idiot. Hold on, people. Let me just erase the whole thing. Wow, maybe I shouldn't have got a little creative with these pictures. It's just going to go to there. Stop, right? And so here's going to be a shell. You know, we could draw like more shells that are more outer, more to the outside. We could draw shells that are more to the inside, whatever. But here's a typical shell. And we're going to have to describe the radius. And then we're going to have to describe the height. Okay? Maybe we shouldn't draw pictures. You know, like maybe I should have kept this vertical line right here and not even drawn the red circle. Oh, whatever. But, so as always, it's going to be 2 pi times r times h. So what's my r here? It's a vertical line segment. So it's basically going to be a y value. And again, this is a very simple one, even simpler than before, because we're just going from the axis out to some y value here. So the radius we're just going to call y. And how are we going to describe the height? This brown line segment, right? Because, I mean, it's not going to be the function, because root x is from here to here. If I solved this function for x like this, okay, now I can describe from the y-axis to the curve. And so from here to here, okay, this space right here, from the y-axis to the curve is going to be represented as y squared. Again, from x-axis to the curve, this distance, this length, okay, would be described as root x. But from the y-axis to the curve, we have to change things up, solve this for x, and call from here to here y squared. But I want this. How am I going to get that? Well, remember, from here all the way to here is 4. All of this is 4. So if I take 4 and I subtract this, I'm going to get my height. So it's going to be basically 4 minus this y squared. And of course, this has to be dy. And these values need to be y values. And again, it's dy because look at the thickness, right? It's a change in y. Change in y. Okay? Now these limits of integration are y values. Again, it's from the innermost shell, 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 all the way until we get to the outermost shell. So it looks like we're going from like here out to here, you know, and so these are y values. So we're going from 0 to where? Where is this intersection? And again, maybe I never should have erased this vertical line, you know, x equals 4. So where is this, okay? And you can basically get that. You might just know it just by your knowledge of graphs and maybe from your graphing calculator, but you could like literally plug in. This is not one of those situations where you would set these equations equal to each other. You wouldn't do that. You wouldn't set y equals root x equal to the other equation, x equals 4. I don't even know how you would do that. But this is not one of those situations where you do that. Other times you do, but not here. Here you would like actually just plug in 4, x equals 4, and you would plug it in to this x and get 2. So we're integrating from 0 to 2 of all that, and your graphing calculator should say ultimately it's going to be exactly 8 pi. And that does it for, you know, we're going to do a lot of practice, and feel free to, you know, ask a lot of questions as we follow up a lot on this, but that's the long and the short of it for the, you know, the new methods like the shell method and all that. But we're going to definitely take a good thorough look at a lot of homework problems and other examples and a lot of extra practice. But hope that helped.